some incremental ensemble Gaussian processes and some dynamic versions, and if time allows, I'll talk about supervised learning and graph-guided EGPs. Okay, we already talked about the uncertainty quantification, scalability, robustness to dynamics through the adaptivity with online recursive algorithms, and we have seen performance guarantees even in adversarial settings. So all of these can be revisited under the lens of incremental ensembles. So to motivate, I will start this part by asking myself, how expressive is a single Gaussian process? Okay. The answer is, in some cases, the more Gaussian processes you have, the better. So another way to look at it is that there are multiple learners that I will index with M, and everyone is taking a view on the function f, and this view involves multiple kernels, a kernel per learner. So basically, an ensemble Gaussian process is like a Gaussian mixture, which is actually non-Gaussian. It's like multimodal. And the idea is that starting from a multimodal prior, we may be able to reach the posterior much faster, rather than starting from a single. So basically, in the RF-based ensemble Gaussian processes, basically whenever we have a different theta m for different learners m, then everyone, the one with superscript 1 is the learner number 1, and the learner number m, and then the meta learner combines the EGPs with weights that basically can be viewed as probabilities of the learner m having a correct description of the function f. So basically, the nice thing about this framework is that it can meet parallel implementations. So basically, each one works on its own, on his or her own, and then they combine, the meta-learner combines their estimates. Okay. So this is the idea. You have a prediction. So the expert M forms a prediction for yt plus 1, given yt, a different one per expert M. Then there is an ensemble prediction where these predictors are combined with weights WETM. And then there is a follow-on correction term where the expert M updates the model for the probability of theta n given yt plus 1 by through the multiplying the likelihood with the posterior. And then the meta-learner updates the weights. Things start again with a new data, plus 1. So if you have a Gaussian likelihood, this can afford order d-square updates, and if there is a parallel computer, then each one can have m equals 1, but altogether multiplied by m. So the issue is, what is the typical way of doing performance analysis with these ensembles? You want to bound the performance of incremental ensemble Gaussian processes relative to the benchmark. So no assumption of the data generation, which means we can afford even adversarial settings. So the so-called negative regret, the so-called regret, is basically the negative log likelihood minus the negative log likelihood, but where we optimize at every time point t. So here, every time you are solving a log yt given yt minus 1, this is it's called prediction loss, right? Loss because it's a negative log likelihood, gain if it was the maximum likelihood. And this is the instantaneous benchmark loss. So standard assumptions, if the loss is convex and continuously twice differentiable, and it has bounded first two derivatives and the kernels are shifting variant bounded, then you can prove that. This approach to ensemble, incremental ensemble Gaussian processes has a regret, which goes down as, it's called sublinear, right? So if you divide by t, it goes down to 0 with the rate log t over t. Okay. Now, I just wanted to take two approaches. I'll skip that one. But the question is what happens if we want to model dynamic function models. So function models that change with time. Okay. How each individual GP learner accounts for dynamics. One approach is using a random walk, which you could generalize by first order state transition methods. So let us suppose that the thetas are evolving according to this random walk model, and then using the random features, our output is a linear function of the state, and then Mr. Kalman comes and tells us that he can do state estimation and prediction, which takes into account the dynamics. So the predictive PDF accounts for the state transition. So look at what happens here. You have, imagine that under the integral you have theta t plus 1 and theta t, okay? And then you integrate out the theta t, so you're getting the theta t plus 1. This is the predictive PDF of the parameter. And then the kernel filter updates are exact with Gaussian likelihood. And you can imagine this thing that we discussed here for the linear random walk model can be extended to extended kernel filters and unscented and particle filters. Okay? So these are some real data to demonstrate how the ensemble Gaussian processes can improve upon what we have seen before. Let's focus perhaps on the most attractive data set, which is out of a robotics experiment, and then normalized mean square error of the parameters and of the output yt plus 1, yt prime minus prediction. It's the normalized minimum prediction error, basically. T prime given t prime minus 1. And then the smaller the better for different alternatives. The dynamic ensemble Gaussian process is this magenta purple curve, which stays lower. The others are the incremental without the dynamic. So this is the blue. That's one reason where you see things change and increase, because the model changes, right? So that's relates to the previous question you asked, why one blue shows up and increase. This means this is a warning for a model mismatch. That means here, if you compare it with the dynamic, that whenever you take into account the dynamics, your normalized mean square error is not jumping up. So this is a deterministic version, iterate here with kernels, multi-kernel approach. And these are benchmarks, abbreviated names of the corresponding algorithms. These are real data. And indeed, it achieves state of the art, this approach with the dynamics and the ensemble. So, if you look at regression and you want to test complexity, let's look again at the Sargos. Here is the again, prediction problem, the dynamic and the non-dynamic, the blue, they do the best. That means here the dynamics are not very prevalent, and but they outperform the alternatives, the competition, which is the SSGP. This is Gaussian process, sequential Gaussian process, they call it. So this is Gaussian process, a single Gaussian process. Here it is ensemble Gaussian processes. So I forgot to say that the nice thing about having a weighted combination of Gaussian processes is that as time progresses, the weights allow you to select some, even a single best kernel that will change eventually in the next time, because the weight would increase or decrease depending on what the data tell you. So this is something for classification correspondingly, and again, the different data sets that this ensemble seems to be doing extremely well. And the corresponding, now what is amazing here is this, the complexity. So this is CPU cycles, and the incremental ensemble GP is this blue, and you see that it's fairly close to the, or better than the competition in terms of running time. So this is the scalability thing. Now, let me take a couple of minutes to discuss how Gaussian processes can be used for unsupervised learning tasks. Okay. So remember here I have X and Y and so on. Here we want to obtain a low-dimensional representation XT for an observation YT. You're not given XT. So the popular approach introduced in 2005 by Lawrence goes under the abbreviation Gaussian process linear variation model, or non-linear. What is the LVM?
Latent variable.
Thank you. Latent variable model. So basically, you look at the dimension D of the vector YT, which is many dimensions. So you have a scalar function of the what we would call principal components otherwise, and we assume that this function of D has a Gaussian prior, and the noise is Gaussian. And then if you look for map estimation of the embeddings, you are called to find the, to minimize the log posterior, or after Bayes' rule, like conditional likelihood and prior. The prior here is Gaussian. The conditional likelihood is the product of Gaussians, but what you want to notice is that the X shows up here, and this is precisely what renders the cost function non-convex, and its typical solvers are conjugate gradient solvers, but again, no guarantees of convergence. And most importantly, because you have them in the matrix, you still get the Kelso dimensionality because you have T-cube dimensionality, and you need to take evaluations of the likelihood and gradients for T-cube variables, so it's really does not scale. Okay, so instead, so if you want to test this, this is the latent variable model that we're discussing. So it broadens the probabilistic PCA, and I explain how it broadens. If you do an experiment where you apply ordinary PCA or probabilistic PCA, then you have these clusters of different colors. You have blues and reds and greens. These are low-dimensional vector X has dimension 2. This is principal component X2, X1. And this is the difference with GPLVM. What you observe here is tighter clusters, better separation of the red with the green, and most importantly, you can afford a gray or black or more gray or white spaces depending on how confident you are, is the uncertainty quantification that is added. And what these people have, or this Lawrence gentleman has proved is that if your kernel is a linear kernel, then GPLVM boils down to probabilistic PCA, which is like PCA but with probabilistic interpretation that I showed earlier. Okay? So the RF-based is something that we came up to fix up the curves of dimensionality that I talked about. And basically, you can adopt a random feature model and treat theta as nuisance parameters. So basically, we are going to have a Gaussian process approximation, which is the inner product of theta with random feature vectors, with Gaussian theta of unitary variance, covariance metrics, or identity covariance metrics. Now the conditional likelihood is like this, but then you marginalize over theta because you treat it as a nuisance parameter. And then the approximation that is involved allows for much less evaluations of the likelihood and the gradients, pretty much as with the supervised versions. But even with unsupervised, the same things carry over. So we can do it in online form. I don't want to spend too much time on it. I just want to demonstrate that how it works with real data. So here I'm showing I forgot to say that pretty much you can add also the ensemble anytime you have an approach with a single learner, you can get a linear weighted combination for an ensemble of learners. And what I show here is classification error rate versus runtime. And what you observe is that the red cross is basically the ensemble random feature based GPLVM. Okay? So very low classification rate in a few iterations, that's the red here. And then if you look at the classification error rate against runtime of USPS, similarly you see the red in the corner down, southwest. So these are all alternatives. I mentioned the GPLVM, the one that I described in some detail is the cross, but in some cases it requires more, about 1,000 iterations, samples. And here what is shown are how the clusters are formed with a two-dimensional. Here is classification experiment, right? So there are 5 clusters, 0, 1, 2, 3, 4 letters, numbers. So there are correspondingly, should be 5 clusters, right? The orange, the blue, the magenta, and the gray. Okay? So, any questions? So basically, I brought into the picture in the last 15 minutes 2 important concepts. One, that you can improve considerably the performance if you take an ensemble of learners without paying too much if you have parallel computing. So each one has its own computer. Clearly, you enhance the space, the expressibility of your estimators, and then you can tackle not only what we have seen supervised tasks, but I moved on to explain how these approaches can even handle unsupervised. Yes?
So do you set the weights in the Gaussian process mixture?
Yeah, you said in the Gaussian process mixtures that when you compute the weights, they perform variable selection. So they do that naturally. You don't have to add sparsity priors or something like that.
No, they're not. basically, I should have, let me see if I can see here, yeah. For example, over here, if you look at this probability is the weight, right? So you take into account the weights, but I think it's much easier if I express it. This is on the dimensionality reduction, okay? I should have gone. Yeah. So you see here, if you stick to a same learner, M, superscript, and you go from t to t minus 1, right? Conceivably, if your likelihood is high, this one will increase, right? But if your likelihood is low, then next time, this learner is not going to have major influence. So it all depends on what the data are telling you.
Thank you, Professor.
Thank you. Yeah. Next to Binucci.
Yeah, so
Francesco Binucci.
Yeah.
Yeah, okay.
see, I struggle to see a transition from random filter Gaussian process to ensemble random filter Gaussian, because in the random filter you already have a posterior over theta, which was Gaussian. So basically you could integrate out theta and have the prediction. So that was the online random filter Gaussian process.
Yes.
So why we should consider particles different thetas if we already can integrate theta? I mean, theta had a Gaussian prior. I thought it was in the last part, in the previous part of your talk. You had a.
I am a little bit, I'm not very clear in what you're saying, but I can address the second question you asked. You asked about why looking at particle filters, right?
No, if you go to the slide in your previous part of the talk, you had that theta has a Gaussian posterior. So basically, you could recursively compute the approximation on random filter Gaussian processes by integrating out theta.
Yeah.
So my question is why we should consider different thetas if we already are able to integrate out theta?
But I did not advocate integrating theta whenever, at what point did I'm a little bit confused, I'm not following the question.
Sorry, I saw in one of the slides you had theta distribution over theta. It was in the previous part. Of the
How far? Unless you want to talk about it later, or I can do it. Yeah. No. Can I suggest we do it?
Yeah, okay, sorry.
The only reason is that it's not much. Let me see. Okay. Oh,
Yes,
last.
recursive random filter Gaussian process.
Ah,
Yeah, it was there. So you have the distribution over theta is Gaussian, so you already have the theta integrated out, right? In the
hold on, let me make it a little bit larger. Oh, yeah. So here we are going from the, we get the xt plus 1, right?
yes.
And then we form the yt plus 1, the predictive PDF, right? Okay? And then once we get the yt plus 1, we get the corrective PDF. So what is the question now?
Yeah, I mean, you see there from the posterior over theta, you obtain the prediction over y, which not depends on theta because you are able to integrate theta. The next.
Oh, you mean here?
Yeah, if you go up next.
Theta, yeah, I marginalize out theta and I get predictive.
Yeah, exactly.
And the reason I did that because I need the predictive PDF in the denominator, right?
Yes.
Okay, go ahead.
Yeah, so you obtain the posterior theta for the next iteration, and you can do the same. You integrate out theta. So basically, you are integrating theta every iteration, right? Yes, exactly.
Yes.
Yeah. Yeah. So
And
basically,
then I update theta. I'm not integrating, right? here I update the model.
Oh, okay, so you're predicting. Oh, okay.
Right. Yeah. I think it's clear. Huh?
Yeah, see.
Thank you.
See. Okay. Of course, I forgot to say, if you are confident that you have reached that state, there's no variation, in other words. Because at some point it may be good enough. You may not improving much. So then you can skip that part and only use the previous one, right? So you don't have to update theta if you are confident that the number of data you have yield an accurate enough. So now I want to talk about.
Can I ask a question?
Sure.
Have you worked on how you choose the dimensionality where you want to reduce your when you use GPLVM, you probably have to pre-specify the dimension. Have you worked on how to choose the dimension?
No, but this is I suspect that this would be an issue like typically it's the computational complexity that dictates that, right? Because in this particular problem I was looking at, I was having a dimensionality reduction. And then the question is, if you have 1,000 features, how many features do you reduce it to, and how do you know whether it's good to go to 10 or to 20, for example? Many people love visualization, right? So they do either to 2 or 3, because you can visualize the projection over that. But there may not be enough. Ultimately, it is an issue of how low is your rank, right? The data can be described by a low rank or the rank that you have. So if you have, so it's like I'm telling you that, so the answer is yes, you can do it pretty much the way that people deal with a low rank approximation. So you basically add the bound and a regularization term of any values, right? If you want to say that I want to have only 3 non-zero eigenvalues, you put the singular vector, and then you tune with validation data your lambda regularizer to get you 3 or 5, whatever. No, I have not done it in this particular case, but I believe that's so. Okay. Now, what is another thing is that graphs are almost everywhere because we have networks. And a traditional popular model is, you will hear more from that, from Gonzalo Mateos and Georgios, that popular approaches are what people like to call semi-supervised learning, because you have nodes, and on nodes you have measurements, which could be scalar or fractal, and they characterize everyone, right? So suppose that you want to predict the vote in the election solved by S, then you know that everyone has an educational level, and he is rich, or she is from the university, or he is blah, 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 what degree they have. They have characteristics, and they're correlated. They have friends, Facebook, or whatever. So you can imagine that interdependencies between nodes on a graph capture correlations. Right? And the issue is, how can I use a graph to help me through with Gaussian processes? Can I do incremental semi-supervised learning? Yes, the formulation goes like this. You have a set of vertices and the adjacency matrix. N is the size of your network or your graph. How many nodes you have, and I forgot to say that typically you observe only a few because you don't know everyone, and many things are constrained by privacy considerations, so you may not be able to check all of them. But nevertheless, you're looking for a real valued function f from the nodes to the reals, because you're trying, given the graph and its adjacency, and given some values on some nodes, you want to find the values on the nodes that are not observed. Just to help you connect with the previous part, you may want to replace in your brain the index t with the node index n, okay? Then the rest of it more or less is the same, okay? So you have nodal values on observed set O, calligraphic. So there's an observed set, and the problem statement is, if I give you the graph and the measurements of the observed, can you predict the values at the unobserved, which is the unobserved U set, which is the vertices set difference with the observed ones. So we are in the incremental setting, which suggests getting the yn to predict yn plus 1, and after that you correct after it is observed. If you want to think or get motivated why this is meaningful as a problem, when is the incremental setting very well motivated? Things like the stock market, right? You don't know the price of the stock, so you need to predict. But then you need to decide on your portfolio distribution of your money across different stocks. So this is clearly a case where the function can utilize what you know, function model can utilize what you know up to n, but then you want to extrapolate to n plus 1. Okay, so here is an idea that actually was originally done in a deterministic setup with, as a lead author was Professor Giannakis, Professor Luz, and myself. So there, we look at the adjacency matrix and pick the row and or the column that node n belongs to. So basically you're saying, I want to find something about the node n, so I look at all my neighbors, what connectivity we have, okay? And if it's directional, you may want to have the row as well, but if it's unidirectional ones, and then utilize this vector of the adjacency matrix as a feature vector. So now you try to solve the previous problem by replacing xn with an. How's that? You know what I told you? All the learning problems you are facing with this trick can be readily mapped to graph-guided learning, semi-supervised learning. That's very unique and attractive. So I told you a systematic way you can take into account the graph knowledge. So we have m learners again, and you remember we discussed this vector example an plus 1 is for a new node n plus 1, which is, we can have a prediction. And this is the predictive PDF with mean and covariance given by formulas as before. And the meta learner combines the information from all learners with weights WM. And correspondingly, you get the linear combination of the predictions and the associated performance. When now yn plus 1 becomes available, you can update the model and update theta n plus 1 as a function of theta n and its performance. And again, similar to what we discussed earlier, we can have an update of the weights that basically depend on, in some cases, the weight of a certain node increases contribution in other cases, it decreases the contribution. But again, thanks to the random feature-based approaches, we are scalable. So here is what the graph driven is GRAD EGP approach versus a popular approach that is out there on graph neural networks. Graph convolution, graph neural networks is abbreviated typically. And here is side-by-side comparison. Oh, this is the incremental, which definitely enjoys reduced storage. You can write on theta, theta, and so on. This is can afford the batch approach, so the storage grows if you increase. You have scalable online updates. Training is definitely not scalable with GCN. Through Bayesian, you get uncertainty quantification that can be easier than point estimation that the deterministic approach will give you with some confidence intervals. You need to do more work to characterize the performance. I would say this one is one of the top. So here, there is no need to have, you can only do inference or learning only with nodal features. But the graph neural networks require model features. So, meaning you need the X. Here, you can do only with AN. Of course, you can augment the AN with XN, right? You can do all of this, but this is a unique feature, I would say. And another nice thing would be some privacy-friendly approach, because what happens, what I didn't stress earlier, is that when you take the features X, XN, or the features AN, and you do sine and cosine, remember when you project for the random features, you take V transpose X and then sine or cosine. If I give you the sine or cosine, you cannot uniquely identify the X that I sent you. So that is what I call privacy friendly when you change this. And then you need to expose the connectivity to of pattern of nodes. So this is the testing approach. This is a synthetic. This is a synthetic stochastic block model. And this is real data. This one is network delay. So basically, you identify packets from origin to the destination for a few origin to destination pairs, and then using the function estimation, you can extrapolate it to know the delay for any arbitrary pair of nodes. This is also important for transportation, right? If I tell you, from here to Belgrade is that many hours. Let's say, I don't know the geography here, but from any big city, if you tell you there are many points A and B, that I know how long it takes to drive from A to B at different time of the day, right? Then I will be able to tell you what, if I know a few, I will be able to tell you what is the delay from any point to any point. How, you will ask. It's clear that the different ones that you have are correlated if they pass through the downtown, right? So then they will incur some delay. So you can take advantage of other pairs that you've measured to infer things that you've not measured. Okay.
Can I ask a question?
Yes. Huh?
I was just thinking, beyond the incremental aspect that you have here, just the fact that you can model your function with the feature, your neighborhood, you encode your neighborhood through the vector AN, I think it was, or whatever you call it. Just in the context of using these GP models with those features, have you checked if again, your predictors are going to be something that's probably going to be linear in that vector, which in a way that makes you, when you multiply with that, or in a product, you're like aggregating probably some quantities from your neighborhood. So then I was wondering if you check if there would be any connection with that model, again, beyond the incremental aspect of it, to maybe a Bayesian GNN or something like that. Or a Bayesian GCN is, if you recover something like that just when you are using your GP machinery on those feature vectors.
Oh, it's a very good suggestion. I have not looked at it. So that you're saying that, yeah, I understand.
When you have your features as encoding the neighborhood, I guess as you are generating predictions, that would be probably something linear on that vector, inner product that quantity, and I guess, which means it's like you are aggregating some other quantities on your neighborhood, and then that's typically what a graph convolutional filter does in GNNs. Plus, you have all the Bayesian aspect to it. So, for me, it might look like, not knowing, just guessing, like a Bayesian GNN, something like that. Bayesian GCN.
But you have to integrate out the axis. Because as the GNN nowadays requires the axis. So the aggregation.
What is X?
X is the feature.
The nodal feature. Yes.
The nodal feature. Here I don't need nodal feature. Only the graph features are enough.
That's fine. But if you have them, why not use it? Suppose
Yeah,
you have
but
them.
I said to fulfill your Bayesian viewpoint, you must be integrating out the axis. So you may be right.
Yeah, I don't know.
Yeah. I don't know. It was a very good remark. But I'll show you a little bit more other things that you can do. So then over here I'm explaining the benchmarks, and the figure of merits are the normalized mean-square error, which is exactly what I said here, n prime minus the predicted one that I have, okay? So the smaller, the lower, the better, and they're in time. So here is basically, the GP is the, so normalized mean-square error, the smaller the better, right? And this again, so this is the synthetic one. Because it was exactly grad GP. This is the grad GP, the blue one, the lower. And then there's a GP which is up here, the dark black. And the KRR, this is a kernel ridge regression. And the grad Raker, this is the heuristic approach. So then you can have this is here to point out the uncertainty characterization. So basically you see that we are very small, we are very accurate in the average, and then we can also tell how the confidence intervals, will play out in our case. So this is where I am arguing that you can, using the grad EGP, you can have uncertainty quantification. And at the same time, you stay within the confidence intervals. Now, this is a beautiful runtime comparison. You see here both synthetic data and real data. Just 1,000 nodes, not that big, but nevertheless, the grad Raker, which is the red, is going to have consistently among the lowest. The last one and the first one, clearly the lowest. Okay. So it is attractive in large scale. Now, the next question that I want to ask is why only the AM? Okay? Why only the column of the adjacency matrix? So can we have more informative graph features than AM? This is what Gonzalo's was trying to ask. And the answer is yes, if you adopt what we like to call EgoNet. So basically, what is an EgoNet? Every node here, the red one, okay, has blue neighbors, but out of the blue neighbors, we're going to record the friends that are connected with one another. So basically, you see the greenish neighbor is connected with this blue, but they're not connected with the red. Okay. So basically, the EgoNet of a node is all these that are contained in this oval. And we have a node N, we have the direct neighbors, the blue, and all edges connecting direct neighbors. Okay. So each EgoNet has its own adjacency matrix, which has many zeros, because everywhere else is basically, it's only the neighbors. So it's a sparse matrix due to limited connectivity, but it has a feature vector, x and ego itself. So the model will use the EGONET feature vector as input, and we're going to look at function values, a function of the EGONET. So this is what I would call graph ensemble Gaussian processes EGONET. And then in the EGONET, you can capture connectivity to all nodes through, and you can include the degree of the node. You can also you can include what is known as centrality, between centrality. And all I'm trying to say is that this x and ego would include eigenvalues of the EGONET. And this particular connectivity pattern characterizes each node. This is called vertex. And you can also do vertex, edge, centrality, clustering coefficient, and other metrics of different vectors, which are detailed in this nice tutorial by Kolaczyk. So our idea is basically to take this vector, which is much easier to handle than graph convolutional networks. So because you're in graph convolutional networks, multiple times you're called to multiply with the adjacency matrix. And I believe that once you've used the adjacency matrix, you don't need to multiply multiple times. So basically, this is some experiments to verify that grad EGP ego is doing extremely well with the performance. So there is GNN here somewhere in GPs and grad EGPs. And then what we can see is that the orange, that it should be the grad EGP ego, performs extremely well. Here is normalized mean square error, prediction error, versus the size of the network and the corresponding uncertainty quantification. Okay, so this is all that I have to say about ensemble Gaussian processes and different aspects of them, graph-related aspects, as well as how we address scalability problems, how we deal with possible dynamics of the model. Now I want to switch gear and look at another very important problem that I believe Gaussian processes offer a very good fit. And I would like to at least cover part of the Bayesian optimization using GPs. There is a bandit setup, blind or black box, and open loop. I don't think I have time to go through the closed loop that welcomes reinforcement learning approaches. But let me start motivating Bayesian optimization. That's the word, that's the popular word, for high parameter tuning. So I don't want you to confuse the X that I was using so far to denote the input features. Here, there will be the hyperparameters. In the context of a neural network, it will be the number of layers, the number of nodes per layer, and the learning rate that you need to use when you do backpropagation. Okay? So basically, you look at the input, the hyperparameters, you train a neural network based on some training data D, that's the calligraphic training data. And then you want to, so you have a parameter theta that you pass on, and you want to test in order to validate the accuracy, right? So, but this is a black box. You don't know how to select the X. This is what is meant by the word bandit optimization. So you want to find this X that maximizes the validation accuracy f of X. Okay? Problem is that you don't know f, right? So if you don't know f, how can you start thinking about any gradient type of approach? So the f is a no. So if you have huge number of point evaluations to find out which one of the combinations of your hyperparameters is an attractive one, it can be computationally prohibitive.
Sorry,
Yes.
but if you don't know f, how do you relate the other parameters to the f?
How do you relate?
Like if you don't know f,
Yes.
how do you know? How
It's
do
not
you,
that you don't know it at all, but you don't know it exactly. So you will see how through a Bayesian model. Okay?
okay, because in a neural networks you don't know, let's say, the shape, but you know at least the analytical formulation.
Yes, but at the same time, if you don't know, you have to try all possible combinations of neural network parameters, and for each combination you have to find the error on a validation set and then select that one, right? But this can be prohibited. That's what I said here. Expensive function evaluations can be prohibited. Enumeration. Okay, so the idea is that you can select minimally informative evaluations by leveraging a Bayesian model. So basically, what you will see here, well, first of all, let's try to recognize where these things are, very nice match for. So suppose we're after discovery of drugs. So the input there are the parameters, the components of what chemical elements each drug has, right? But what we measure as output Y is basically your immunity to COVID. Or let's say this drug is for diabetes, right? The measurements you are having is basically the insulin or the glucose level. So you see directly. You have 5, 10 elements that you can mix and match, but you have to try all kinds of combinations, right? And likewise, suppose that you want to employ an IoT or sensor network, the geographical locations of the sensors, you cannot try everywhere in order to make sure that the interference that is being caused to communicators in this region is not huge, right? So you have to try all possible things. So what is the idea? The idea, under the name Bayesian optimization, goes like this. You build a Gaussian surrogate model for f of x to guide the acquisition of inputs. Okay? So, xt, remember, is the hyperparameters, or what I don't know. So, what I'm going to try to do is to find this f, or an estimate of this f. And then, once I have an estimate of this f, that estimate and its uncertainty will guide my selection of the next xt plus 1. Okay? So there are two steps. One step is to update the function model, f of x given some data. And this data are the previous data plus the xt yt. Okay? Now, you enter, so the function model is like this. You are after the p of f given dt that will help you move on to y given dt. That's pure, like the Gaussian process model. Now, the candidates can be many. The GP, the ensemble GP, the random forest, or whatever you have. Then you need an acquisition function. The acquisition function basically, or acquisition criterion, alpha t plus 1, should be the expected value for all possible y's of a utility function that depends on the input and the y. Okay? And it should be inexpensive to optimize, ideally with closed form, the A. Now, and the choice should balance exploration with exploitation. Why? Suppose that I have come up with 5 evaluations of my f of x. F of x1, f of x2, x5, f of x5. Okay? The question is, which will be my x6? If the f of x5 is the highest, someone may be tempted to say, okay, look around the x5, you may get higher. This is the exploitation. But you need to be risky at times, because you may not be unimodal, you may be multimodal, and you may want to go sometimes further away to explore the search space. And this is what is meant when I say balance exploration with exploitation. Okay? Now, let me give you with a picture what is the beautiful idea behind the Bayesian optimization. Suppose we are at t equals 2. I am showing 2 pairs. This one is x1, y1, and this is x2, y2. Okay? For reference, because this is a synthetic example, I am telling you that the true function is the dust. Okay? The first step, what Gaussian processes will do, will be to create an average, an instantaneous average function, which will look like the solid line. But I want you to notice something else, that around the solid line is the uncertainty shaded area. And sure enough, this is a big distance that you don't have sample points, so the uncertainty is much higher here, rather than there, okay? Now let's look at the criterion, the acquisition function, okay? The acquisition function has a maximum at this point, shown by the red triangle. This is over x, right? So this is suggesting to you, if this is the function a, and this is the maximum of this function, it suggests that you collect a point here. Okay? This is not exploitation, because exploitation would suggest something around here, and something around here, or something around here. It's not exploration, because it would have suggested bigger certainty here, right? It's kind of trying to balance. Okay? Another sample comes, bingo, we asked we went to the red, and we asked the y2, the y3, I'm sorry, sample y3. Look at how things have changed slightly, right? Here, we're very confident because we have 2 points rather close. This is, okay. So now look at the function a of x, the acquisition function. That's the maximum, right? So this is the new thing where we're going to sample. And if we sample there, this is our red sample, the y4. This is the posterior mean, I forgot to say, this is the posterior uncertainty. That is the picture. And as you go, you're going to select the most informative data x that will allow you, with a few number of samples, to come up with a desirable solution to the optimization problem. Okay. This stuff, well, this stuff you should know by now. So we start with the Gaussian prior, the kernel kappa, we assume that the likelihood is factorable, that leads us to the posterior, everything is Gaussian, so the posterior is Gaussian. So we get mu tx, so that's the conditional expectation, that's the mu tx, okay? That's how you find the solid line we talked about in the previous picture. And this is how you find the balloon, the uncertainty balloon. So this uncertainty is what guides the selection of the next x. Because this uncertainty, this combination of mu t and sigma xt will basically offer you the exploitation versus exploration. So if you want to do exploration, you adopt the variance only. If you want to do exploitation, you utilize the mu. And over the years, there have been a lot of approaches. Let me give you one of the early ones that has been the workhorse for Bayesian optimization in practice. So here is your acquisition function on the expected improvement. That has been very popular. You take the expected value of the probability density function over the PDF of the posterior of f of x, and look at what you're doing here. You're looking at the maximum of f of x and t. So if f of x is greater than t, your tau, would be the maximum of whatever you have observed up to now, then that means that if you are bigger than t, then you are attractive. But using the Gaussianity, it so turns out that the expected value becomes available in closed form, and it contains one term that has the variance of the estimate x, and another term that has the Gaussian PDF. This delta is the distance from the maximum of your conditional mean. And this is the delta. And this is basically the CDF, Gaussian CDF. So this is a way of balancing exploitation for exploration. Here, as I said already, this is the exploration parameter. The higher the sigma, the more risky you become to explore. And the higher the delta is the exploitation. The smaller the delta, that means you are conservatively staying close to the existing maximum. Okay? Now, one of them that got the Test of Time Award in ISAML 2020 is Gaussian process optimization in the bandit setting. And basically suggests that you take a convex combination of mu t, which is the exploitation parameter, and the sigma t, which is the exploration parameter, and the constant depends on this beta constant is basically controlled by the different choices of the beta that they justify different application domains. But it's up to the designer to choose. Okay. I want now to tell you my favorable one. This is by a gentleman called Thompson. And this gentleman discovered it in 1964. It's beautiful in its simplicity, in my mind. Okay, so this is called posterior sampling, probability matching. It was revived in 2014, but the original guy is this guy, Thompson. Okay, so this guy says the following. You get your favorable function estimation to estimate the surrogate function, right? Your GP, your neural net, or whatever, okay? But the GP is beautiful because it's probabilistic. So you know this posterior. So what you do, you draw a sample from this posterior. This is called Thompson sampling. Why is it good? Because if your mass is concentrated around the mean, most likely your f of x will come from this, right? From the close to the mean. So it will be exploited. However, you do it randomly. So this randomness will buy you exploration, right? So this is the basic idea. So the sample randomness guides exploration, no other design parameters. It's very simple. So this guy also advocated doing the same thing for the RF-based approximation. So in this particular case, you don't need even to draw the F, you draw the theta tilde from the posterior of the RF. And then this is readily extendable to parallel or batch evaluations. And there are other methods, I don't want to spend time. A lot of information theory metrics. Of course, our idea was to demonstrate that how much more you gain with ensembles, so you can get ensemble acquisition functions to balance this. I don't want to spend time. But I wanted to talk about this one. This is something fairly recent because it answers the question, how can we come up with effective and efficient, computationally efficient choices of GP surrogates? Okay. So the idea is to couple EGP with TS, so Thompson sampling. So basically, this is what we are after. So the meta learner picks up an EMMA, a learner, from a categorical PDF, CAT is for categorical, of a set of learners, each weighted by WTM. So we draw. So it's a PDF, right? So you draw, we set the probability, you get M equals 5. So the number 5 learner, okay? Then you use Thompson sampling to find xt plus 1. So you take the theta that you draw from the posterior of theta M5, theta 5, the fifth learner, you draw from him. Then you take the inner product, and then you can readily maximize over X, right? So, you can do gradient or whatever. And then you use xt plus 1 to obtain yt plus 1 function evaluation. And then you rely, so you augment rather all the data, you hit the t and you add the xt plus 1, yt plus 1. And this way you update your weights and your models. I forgot to say that you can repeat the S1, S3 with b times. So it's like you draw multiple times, and whoever gives you the highest inner product of phi with theta, you choose that thing, right? So the nice thing we have managed to do is to prove that if you look at the Bayesian regret, which is the difference between the optimum and the one that you have with your choice xt, then you can basically bound it with, it is with high probability log t times t to the eta plus 1. And whenever you have a batch, you have a rho b, which is a constant, and it's higher. So this global convergence establishes sublinear regret in T. And this sublinear regret, when you are solving a batch, EGPTS is higher. So if you want to test it on synthetic functions, let me see, as I said earlier, here what we are looking at is the simple regret versus iteration, simple regret versus iteration. That's for this first column. These are different data sets. So the red, which is the lowest and therefore the most reliable, because the smaller regret is, where is the, yes, here. The red one is the EGPTS, the one that I described, simple with a lot of combinations of letters. So simple itself, if you use the TS, that's worth checking. If you look only the GP and TS, this is the dust, is very high, 2 orders of magnitude worse. So the EGP helps a lot. That's what you learn from this one, right? That the EGP, the ensemble, helps a lot. The magenta and the dotted is the same. With bandit bio, yeah. Basically all competitions are here being compared over here. Now there is other real data. Whenever you are having a two-dimensional or four-dimensional set space, and the three-dimensional comprises the 2D coordinates of the robot and the push time, how far basically the robot is trying to push an object to a specific location. And then these are the variables that we have to control. And the simple regret is basically indicating again that the EGPTS, which is the red, does the best. And here is for hyperparameter tuning of a two-layer feed-forward neural network. And this is the comparison of classification rates. You can see the EGP goes to consistently at the highest level, except for one case, the bandit dio of the iris, that were very close to the optimum. But in most cases, we are the highest. This is another interesting direction of the Bayesian optimization that involves basically categorical inputs, okay, as well as hyperparameters. So first, you need to learn the best model. Which one is the best model? C. So you have a number of models, and it's optimal hyperparameters. Okay? So you may have neural networks, you may have convolutional neural networks, you may have whatever, right? So you blend them together. So you have a Bayesian optimization that can help you include categorical inputs. Very recently, it has been something attractive. The bandit Bayesian optimization combines Thompson sampling acquisition and multi-arm bandit. I just wanted to say that the first step is to draw for each and every value of the categorical variable C. It has capital C values, okay? You draw for this particular FC, you have the posterior that you have calculated with the data, C, and you find a value. Then you go and search over all XCs, for example, during grid search or what have you, for all the C's again to find which point you would have selected, the X tilde C. And then for the T+1, you're going to have this CT+1, which is the one, CT+1 will be baptized as the C that yields the maximum of this realization. And correspondingly, the T+1X will be the one you found for the CT+1 winner. If the CT+1 is the number 5 value, then you go to the X5 and you replace this XT+1 with the X5 and augment the data that will help you go back to C1 and update your model. So you can do performance analysis. I don't want to get into that. And you can test. I wanted to basically come back and to deliver what I promised, that this Bayesian optimization can be very useful for managing networks. And either IoT or mobile edge computing networks. Okay? So if you look at the definition, what is mobile edge computing? Is a platform that provides cloud computing capabilities in a radio access network and that they are in close proximity to the mobile subscribers. Okay? So, what are the attributes of MEC? It releases the computational capacity to radio access network and jointly manages wireless communications and computation. So how you compute and how do you communicate. Challenges are abundant. You have time varying channel conditions. Mobile is the first term, stands for mobile. You have heterogeneity of wireless channels. You have dynamic computational capabilities and load of edge servers. Okay? You can think of edge servers as being either laptops or desktops in your house or in your building. And for an IoT, the wireless device could be your cell phone or your speedometer, what have you. Or you can think of a Mac server as being a base station, right? And then all the cell phones, wireless devices are reporting to this base station or to a bunch of base stations, okay? All right, here is how we formulate it. It's a paper that is going to appear in a cinema. So this is fresh off the oven. So here is what I was talking about. We have wireless devices, WD1, WD2, WD3, and WDM. EMMA devices. And servers. Mac server 1, 2, N. So the wireless device, which is your cell phone, produces data, information-bearing data, and it is characterized also by certain load in its CPU cycles. Okay? I'm going to use a local computing indicator for the edge computing server if at slot T, your device M, the Mr. Wireless M, communicates with the edge server N, this guy will be N. And because I have the option as wireless device to do computations myself, I will designate the index 0 for this case when the computation happens at the wireless mobile device. Is that clear? Criterion: energy delay cost per WT M per slot M. Okay. This one represents the speed of device M, velocity or at time slot T, local computing, how fast. How much does it cost to do fast computations? That is proportional to the square of the frequency. These are, we found out from real data, it's not our stuff, people here tested those things. There is a constant, and the CPU load times how fast is your phone processor is what controls this energy cost for local computing, at the WT local. And then you have a delay cost, so how long does it take, right? It is the load that you have times how fast is your processor, or inversely proportional. Clear? Okay. Now, suppose that I want to go to the edge computing. You need to start from M and put power PTM to send and reach an energy guy. So that's the energy when you want to do edge computing at the edge servers. So transmit energy is the product of power times for how long it will take you, and transmit delay is correspondingly depends on the capacity where the channel will come into picture. H here, Mr. Bandwidth W, we know the capacity formula. And here's the number of loads you have to multiply, right? And that will give you the delay transmission, okay? The overall delay will be transmission and computation. And the computing delay correspondingly depends on which and how many wireless devices we're going to use the processor at the edge. Okay? Okay. Now, the symbols get a little bit messy. I don't expect you to follow each and everything, but I want you to follow one thing, or two things now. We want to maximize a criterion that depends on C. These are the categorical data, that's why I call them C. I remind you the categorical data are from 0, 1 up to n, right? Depending on where. Then we have some continuous variables, which is the speed and also the power. This is analog amplitude variables, not categorical. Okay? And then there is a system state that I don't know. This is what brings me to BO, Bayesian optimization. I don't know those things. If I am the server, right, the meta learner, I don't know all these things. I don't know how the channel at that point, at that slot will be. Because many times you're trying to play catch up, right? By the time that you solve the channel estimation problem with training, the channel may change, right? So it is a latent state of your model which necessitates, this is the question that you were asking, this one necessitates, for sure, treating it as a black box optimization. You don't know the function f, because you don't know the system state that depends on f. So the challenges are, you have a banded feedback with a known system state, and the things are combinatorial, because you could have solved this problem for all possible states, and you can imagine what I'm saying. And the most important part is that you need to decide per slot xt your continuous variables, the categorical variables and the continuous variables before knowing ftxt, right? You don't know this. Of course, after you've done and you plug, you know how good or bad you did. So this motivated us to look at an interesting problem where you try to solve Bayesian optimization problems that involve categorical variables, finite alphabet, and analog amplitude variables. And basically that led us to something very beautiful, that you need to define kernels over hybrid spaces. So basically your kernel xt, x tau prime, should be the summation of kappa c for the categorical and kappa z for the continuous analog amplitude variables, and the products. So you understand why, if you think about it, although we have introduced it in some sort of ad hoc manner, this makes perfect sense. You don't want to have the sum of the two only, or the product of the two only, the two kernels, okay? Now, for continuous variables, this is a very meaningful kernel, right? Because what does it say? It says that you have a Gaussian bell. One is the z tau prime, which means that if they are close, then the kernel is high, the covariance is high, right? Now, the next one says that if the kernel, the categorical is used by, if this is multiple ones are equal for tau, so consecutive tau prime, this is a temporal thing, then you should sum up well. But if you think about it, the product and the sum, it makes perfect sense. Our novel thing also is that we introduce kernels that account for temporal dynamics. So we take this kx and we multiply with the k temp factor, which basically is when you are too close, basically the k temp is close to 1, right? Close to 1 minus rho. But when you're too far, then because this is less than 1, this is 1 minus rho, then the dependence will go down, right? You're not related too much. And also, we're going to account for contextual information. So basically, we have contextual information will come from the different states that you've observed, right? How do you characterize two states to be equal? So these are really important design parameters that we take. This is our novel stuff. And we basically demonstrated by using a weighted DGP with categorical variables and subsequently continuous variables, how we basically, in this flow chart, we update the surrogate model and the map reward, which is basically what allows you to update the categorical variables. And then you get a new C and a new Z. And then through the map, you get the CP. And then Bayesian optimization, as I described it, will give you the new ZT, and that will help you evaluate the new, or update the new surrogate model FTZT. Okay, and this, with this I approach the end of my presentation. So this one, we had numerical tests over some real data. This is accumulated regret, so the smaller the better. And the proposed time-varying Bayesian optimization and contextual optimization. So you see here that the best one is the contextual time-varying yellow. So that one is the black. The Bayesian optimization is the magenta, so fairly high. And we have two types. Variation of system dynamics that will show the difference of the of accounting for how things change across time. And then whenever you have small variations of system dynamics, all these, the contextual and time varying do not help too much, but still we are the lowest. So if you decide to do either multi-arm bandit, which is only for categorical data, or if you do bandit convex optimization, which does not take into account the categorical data, then you're going to do considerably worse. So the purple is the attractive one, and the other two are with variations. Oh, this one I don't need to talk about. So this is whenever you get reinforcement learning, you can look at the references basically. So summarizing remarks, I talked about GP priors for parametric random function models. I established DNN links and uncertainty quantification. Okay. Then remember that a lot was gained through the intervention of Mr. Fourier, which allowed you to use random features, and that term linear parametric approximate models offer linear parametric approximate models of non-parametric functions for online learning with scalability, and the deep GP for richer model expressiveness. I also advocated after the break the Ensemble GPs that offer wide applicability to operational environments. There is online expert refiner with performance guarantees. Basically, it will tell you how each learner contributes. There are robustness to a model, global and local dynamics. And I demonstrated how not only supervised but unsupervised tasks and semi-supervised tasks over graphs could be accommodated. And the open learning led me to this Bayesian optimization using Gaussian processes and several Gaussian processes. And the interactive ones that I didn't have the time to present could be of interest for cases where you have closed loop. Because there, you also, for those of you that know what is reinforcement learning, it boils down to a value function evaluation. So you want, again, to estimate with every policy, so succession of decisions. So how can be obtained in an optimal manner? And again, the value function, if you know how to approximate it with a surrogate, that can lead you to a novel reinforcement learning approach. Outlook, I talked about wide neural networks and deep neural networks. It would be great if someone could formulate the problem where he can say that for this task, you need to have 3 layers wide and 5 neurons per layer. So it's kind of, as I said, in my mind, the width is related to GPs, Gaussian processes. The wide end of what Gaussian looks like. That's why, if you don't want to go too wide, it is very useful to use Ensemble, so you use the best possible for those. And the same thing, you can argue that you can have for the deep processes. So, I didn't talk about federated or distributed learning. I also touched upon, if you remember, I touched upon the applications to IoT monitoring. Oh, the monitoring. What is a monitoring problem? I just had a very simple example with, if you remember, very simple example with air pollution. Right? But then over that, where you have a sensor network, let's say, and you deploy it, and you want to find what are the optimum positions that I use the sensors in order, for example, to minimize the delay.